This podcast is not meant to be professional advice of any kind. It is meant to be informative and entertaining. If you make any changes to your life, see the appropriate professional before you do so. Welcome to Super Age. My name's David Stewart. I am the founder of Ageist and your host on the Super Age Show. We talk about how to live healthier, how to live longer, and how to be happier. And who doesn't want that? Today's show is brought to you by Inside Tracker, the dashboard to your inner health. Go to insidetracker.com/ageist, save 20% on all their products. The show is also brought to you by Element, LMNT. My favorite electrolyte mix. It's what I put in my water in the morning, and it's what I put in my water at the gym. Go to drinkelement.com/ageist and receive a free 8-serving sample pack with any purchase. Today's show is also brought to you by SRW. Aging is inevitable, but how we age is chiefly a matter of our choices. If you go to srw.co, you can save 20% on all their products by using the code AGEIST20 at checkout. Welcome to episode 132 of the Super Age Podcast. It is great to have you with us. This is going to be dropping on May the 4th, 2023. We are back in the mountains of Park City, Utah this week, and the Ice Age has ended, where some of the mountains, they got 900 inches of snow. So now we're in the mud season, which my guess is mud season is going to go on until August. There's a lot of water out there right now. So that's kind of, but it's still really beautiful. There's like snow in the mountains, and I love seeing the snow in the mountains against the blue sky with the green grass down below. I don't know, I have visions of Heidi in the mountains or something. So we did a couple of really interesting things this last weekend. Mostly what we did was we planned out like the next 2 years of our lives, my wife and I, figuring out like, okay, where we're going to be. We're going to be in New York this block of time. We'll be in Park City this block of time. These are the vacations we're going to take. These are the family people we're going to see. This is when we're going to do it. These are the friends we're going to see. And this was a bit daunting, to even think about making those kind of commitments. But after it's done, it's like, oh my gosh, this relieves so much like uncertainty, and also gives me anyway a lot of energy. I feel so excited about all these things that we're going to do over the next 2 years, and we actually got plane tickets and stuff. So, hey, pro tip: if you book an airplane seat like way in the future, the plane's empty. You can sit wherever you want. You can get any hotel room you want. So here's a plug for planning. And something I wrote about in the newsletter this week is that, one of the things that we sort of planned out is we have sort of a couple of, like a few sort of dreamy things that we want to do. Like we've been to Japan a few times. We want to go to Japan in the fall of 2024. But I think that so many of us, when we set these sort of like, I hate the term bucket list, it's just a horrible term, but dreams, like the sort of things that would be really interesting. We often don't have enough of them. Like there's like, here are the 5 things. Why stopping at 5? Go for 100. And why have them be small? I mean, you don't have to go to the moon, but I think that there's a lot of things that can happen in a lifetime that, if you plan on it and you make the preparations, the logistics, the finances, the scheduling, all that stuff, like you can really make it happen. What they always say is there's a lot more that we can get done in the long term than we estimate, and a lot less than we can get done in a day than we estimate. And that has been my experience for sure. Today's show is brought to you by SRW Laboratories out of New Zealand. Their vision is to extend human health span. SRW Labs curates the very latest in science and research to formulate premium nutraceuticals that support your cellular health, especially as you age. Working with their scientific advisory board, they seek to understand and address the causes of aging at a cellular level, providing support across 12 bodily systems with an approach that is unique to SRW. They know that doing one thing well, such as eating healthily, won't have the desired effect on your health. This is why SRW seeks to educate people on the factors that influence aging and, more importantly, biological age. Use the code AGEIST20 at checkout and save 20% off any order. Go to srw.co, not .com. Use the code AGEIST20 at checkout, save 20% on all their products. Today's show is also brought to you by Inside Tracker. Created by the experts from Harvard, Tufts, and MIT, Inside Tracker uses the power of your body's biometric data to reveal to you what you need to live longer, healthier, and happier. I've been using Inside Tracker for a few years now, and it is the dashboard to my inner health. It's a critical part of my health and wellness routine. And since May is Women's Health Month, Inside Tracker is unveiling an upgraded ultimate plan that includes 3 new hormone markers that are critical to measure during a woman's reproductive and menopausal years. For a limited time, our listeners can get up to 20% off Inside Tracker's new ultimate plan, complete with estradiol, progesterone, and TSH. With Inside Tracker, discovering what your body needs is no longer a guessing game. Visit insidetracker.com/ageist, save 20%, and we'll leave that link in the show notes. This week on the show, we have Matt Yousefzadeh, PhD, working in Columbia, doing some of the basic research on the new field of senolytics, which is really interesting. We're hearing a lot of talk about senolytics these days. So Matt's going to hip us up into what this is, how it affects us, what are the sort of useful things that we can do out there. So we're going to give Matt a call in just a moment. But before I do so, I just want to remind everyone that after my conversation with Matt, we have that little fortune cookie thing we do called Just Try This. A little tidbit to help you live a little healthier, a little longer, and a little happier, hopefully. Let's give Matt a call right now. Hey, Matt, how are you today?
I'm doing well. Thanks for having me.
Yes, absolutely. You are a rising star in the field, and we're really happy to have you on the show today. Tell people a little bit about yourself. What's your background? Where are you right now?
So right now I'm at the Columbia University Medical Center, and I work in the Center for Translational Immunology, as well as the Center for Healthy Longevity. Currently, I work as an aging biologist, but previous to that, my background was working in the field of cancer. But for the last 8 years, I've sort of been studying the mechanisms of aging that drive aging and how to sort of target aging.
You mentioned, did I get this right? Translational immunology? Did I get that right?
Translational.
What? Help me. What is that? I've never heard that.
So there's really sort of hardcore basic science of doing basic biology for the sake of biology. Translational has an eye to sort of take the things from the benchtop and get them to the bedside, or get the, things that we discover into the patient to help benefit them.
Got it. Okay. And so you're interested in the biology of aging.
Yes, very much so. As well as how it sort of relates to the biology of aging all throughout the body, but especially the immune system.
Absolutely. As we know, one of the greatest risk factors with COVID is age, right? Poor functioning immune system. So tell me, how did you come to be interested in this? What were you doing beforehand?
So before, I was studying the field of cancer and really how our DNA is repaired, and how if our DNA is not repaired, it can create an environment that's permissible to the formation of cancer or can exacerbate cancer. Well, as I sort of finished up my graduate work on that project, I shifted to studying how DNA damage could drive aging. And in particular, really wanting to see how DNA damage can induce this phenomenon called cellular senescence, which is a very potent driver of aging.
It would seem that there's a very clear correlation between age and cancer. Older people seem to get more cancer than young people, obviously.
Correct. Yeah. Age is pretty much the predominant risk factor for all diseases. Sometimes more than lifestyle and genetic predisposition, age tends to trump all.
Yes, absolutely. And there's a term that gets thrown around out there called inflammaging. So the intersection of inflammation in the body and aging. Could you explain that to us?
Sure. So inflammation in certain cases can be quite helpful. Say you have an infection or there's a pathogenic condition going on. Inflammation can signal to the immune cells in your body to come in and take care of the infection, clear it out, and resolve it to start the reparative process. However, as we age, we start to build up this low grade chronic infection that sort of persists in our body, even though we don't have an infection, a cold, or a virus always going on. But yet there's this low grade inflammation. And when we have these events that can trigger inflammation, it can massively increase the amount that's there. And that's what's known as inflammaging.
Is there a relationship between this chronic inflammation and something you mentioned earlier, senescence?
It actually goes both ways, where inflammation can activate this state of senescence, and senescence, or these senescent cells, can produce inflammation. I should take a step back and say, what is a senescent cell? A senescent cell is typically, it's any of the cells in our body. They can become stressed out from damage that occurs within or outside of the cell. And what happens is these cells, they will no longer sort of proliferate, grow, and divide, but they still persist. They're metabolically active. And what happens is they're producing a lot of this inflammatory material that can cause local as well as systemic inflammation. It can, disrupt the normal function of our tissues, as well as start to impair tissue regeneration too. So it can sort of disrupt the healing process as well.
Mm. And I've heard this described as sort of the bad apple syndrome.
Yeah.
Right? If you have like one bad apple, it affects all the other ones.
So these senescent cells, they make these inflammatory molecules and they release them, sort of secreting them or dumping them out around you. And so it can disrupt not only the cells nearby you, but far away. And so we always use it's a really tired analogy, but we love to use it, that the bad apple spoils the bushel. Well, that's what senescent cells can do to the other cells around them in your body.
And this idea of the senescent, and I'm going to call them just zombie cells, because they're alive, but they're not really functioning normally. Does this have to do with my understanding? I'm probably way off base here, but my understanding is that there's something called the Hayflick limit, right? Your cell line can only reproduce a certain amount, which is related to the length of your telomere. And once it gets to the end of that, that's it. And is that a senescent cell, like a zombie cell, or is this zombie cells come from something else?
No, it's a really good question. It's all sort of interrelated, but they all come with caveats. So we jokingly refer to senescent cells as zombie cells, and that's because they're really resistant to cell death. So they're turning on these pro-survival pathways, much like cancer cells do. That's why they sort of acquired the nickname of zombie cells. You're right that, the first evidence of senescence was discovered about 60 years ago by Leonard Hayflick and Paul Moorhead. And what they saw was the longer they grew cells, the telomeres, sort of the ends of the DNA, kind of like the ends of your shoelaces where they have the plastic capping on them, they start to erode over time. And eventually, when you run out of that plastic at the end, the shoelace frails and falls apart. Well, that's the case that can happen with our DNA through sort of telomeric erosion. And this is the first evidence of sort of this thing called replicative senescence, or senescence that occurs with cell replication and proliferation. However, there's a lot of cells in our body that they're not always constantly dividing and proliferation. They're sort of known as post-mitotic cells, or cells that are no longer in that cell cycle, constantly growing and dividing. And those still experience cellular senescence, and it's not due to telomeric erosion. It could be due to things like DNA damage, oxidative stress, a number, disrupted sort of recycling in the cell, which is known as autophagy. So there's many things that can cause cellular senescence, but replicative senescence is sort of a really specialized case. And that really affects the dividing cells in our bodies, but we also experience senescence in the non-dividing cells.
Mm, okay, I didn't know that. Okay, so senescent cells, bad. We want them gone. We want the zombies out of our body, which brings us to something called senolytics. So what are these?
That's a really good point. So I will add, backing up, that there are positive times in your life where you want senescent cells. During development, they shut off the developmental cell program and they're taken out, or they can be important for wound healing. But as we get older, we start to accumulate a number of these senescent cells all throughout our body, and they can have quite deleterious effects. For a long time, we just thought these cells sort of tracked with aging and they were in the body. And what we found over the last decade or decade and a half is that these cells can actually be causative of aging. They can be pathogenic in their own sort of fashion. So, and like I had said before, that those senescent cells, they're refractory to cell death. They don't want to die. They want to, stay alive and make garbage. So, what you can do is sort of understand how they are surviving and target those survival pathways. And that's what senolytics do. They're basically a class of drugs that's specific to target senescent cells and the pro-survival pathways in order to sensitize those cells to elimination.
So how do we make sure we're getting rid of the zombie cells, but not the good cells?
So that's a really good point, is that we need to understand these pro-survival pathways. And many of these pro-survival pathways are not always turned on or turned on to the same volume in the quote unquote normal cells in our body as they would be in these senescent cells. Don't think of sort of expression of a gene or a pathway as a light switch on or off. Think of it as a dimmer switch, and sort of to steal from this is Spinal Tap. Senescent cells sometimes have them cranked up to 11.
Okay. So you mentioned the word autophagy as a method of eliminating these, or I guess recycling the proteins. What
Yes.
is that?
So autophagy is a really intricate system in our cells to recycle proteins, micronutrients, and it's really important for things like starvation, in order to prioritize or break down old and dysfunctional proteins so that you can then reuse the amino acids to build new ones. If you think about most of the macromolecules in our body, all but one are broken down and recycled. There's only one that's repaired, and that's our DNA.
And I have heard things like calorie restriction cause autophagy. And so the point is that of this calorie restriction then would be to act as a senolytic, removing the zombie cells?
No, so I think there is, and so what I should say is there's a number of these pillars of aging, things that drive the aging process. Cellular senescence being one of them. There's DNA damage. There's dysregulated autophagy, things like epigenetic aging, and they all interconnect with each other. So senescent cells can sort of disrupt normal autophagy. Similarly, prohibition of autophagy can drive senescence. So there's sort of interrelation that's there. And what we know with like things like caloric restriction, where it has a benefit on autophagy, it also has a benefit on reducing senescent cells, as well as the circulating inflammation. So really, some of these interventions that we see are impacting all of these pillars of aging.
You mentioned there that senescent cells will in themselves interfere with autophagy?
Yes. They're known to sort of have disrupted autophagy as well.
Oh, another reason to get rid of them. So, what are you finding in? Let's talk a little bit about your work. So, you're not doing clinical work. Clinical work means, like you're a doctor and you're treating patients. What is the nature of your work?
I do much more basic biology and preclinical sciences. So I like to understand the mechanisms of aging biology. So how does aging occur? How does it occur in certain tissues versus others? How do these different tissues, or we say inter-organ communication occur. In particular, I've done a lot of work on aging in the immune system and seeing how our immune system ages. What does it mean for the rest of the body? And a lot of the way we do this is using preclinical models of aging. So we can use mouse models of aging, mice that age longer, mice that age slower, and just as well naturally aged mice. Or we can say, let's age a particular tissue at one time, in this case, the immune system. And so what we see is, if there's DNA damage that occurs only in the immune system, it can cause those immune cells to become senescent and dysfunctional. And in time, it can eventually cause senescence throughout the rest of the body, sort of the liver, the kidney, the muscles, and it can overall impact the health and lifespan of those mice. And so really what we're finding out is we're translating from these animal models things that are quite relevant to what's going on in our bodies, either you or I. And we're also using it as a ground to understand new drug targets and possibly test new therapeutics and in new indications.
I know that there are some people out there who feel that the immune system is really the name of the game, especially the thymus. Who I know Greg Fahey and the TRIM trial. So they're using, I believe it's metformin, human growth hormone, vitamin C, DHEA, I think. With the target of regrowing the thymus. The idea that as you get older, your immune system in your thymus shrinks rather dramatically, and it's unable to deal with a novel pathogen. Example, COVID. Do you have any thoughts on this?
Yeah. So my understanding with I think it's like the TRIM trial of what they're doing. They're sort of throwing the kitchen sink at the thymus to try to rejuvenate it. And really what's important about the thymus is it's your savings account for naive T cells. It's these naive cells that are basically used to respond to pathogenic challenges. And once you've exhausted them, you've exhausted them. So once we hit our early to mid 20s, that's it. That's the prime time for the thymus. After that, it sort of starts to, it's called involute, or sort of shrink, and it just becomes this empty bag of fat as we get older. And so you lose over time, we lose that naive T cell pool, and you gain these sort of memory T cells. They've already experienced antigen or sort of a challenge. And so, we're losing our capability to respond to new challenges as we progress through time.
You have any thoughts on the efficacy of what the TRIM trial and what Greg Fahey's doing?
I haven't sort of experienced enough or read enough about it. I know what's going on. I haven't seen the data, so I can't say I'm comfortable to speak on it. But, I'm excited for people that are trying to test and rejuvenate things and trying it a number of different ways. Maybe they have the right way to do it. Maybe somebody else has the right way, or maybe they both have the right way and it should be done in combination. So I always look at it that way of, one of the things that from the longevity perspective that's been interesting for the immune system is there's a drug called rapamycin that many people in the aging community are quite interested in. It's found in the bacteria on the soil of Rapa Nui or Easter Island. And it inhibits this enzyme called mTOR. And it's used in the clinic predominantly for immunorejection and organ transplant patients or for cancer, but that's typically given in very high doses to sick people. However, if you take rapamycin at a lower dose and you give it to mice, it extends their lifespan. And it's done this in other organisms as well, too. It also reduces some age-related pathologies. And speaking on the human immune system, there was a group at Novartis about 10 years ago that gave rapamycin to elderly individuals. And what we know about elderly individuals is they had very poor vaccine responses. So sometimes compared to a normal person, they're getting double or more than the dose of vaccine that a younger individual would be. And they're still not generating as efficacious of a response. So what they saw was when they gave the elderly a version of rapamycin and then gave them the annual influenza vaccination, they made 20% more antibodies against influenza, and the immune cells, their T cells, showed reduced markers of exhaustion just with the short course treatment of rapamycin.
And is this related to senolytics, to removing the senescent cells? I'm not entirely sure how rapamycin works.
No, so mTOR has a lot of different effects. We would say that senolytics specifically target senescent cells for elimination. There's a class of drugs that function to suppress the inflammatory potential or deleterious effects of senescent cells, but not get rid of them. And those are known as senomorphics. And so rapamycin would have a senomorphic effect in the context of senescent cells. So it's not getting rid of them, but what it is reducing their phenotype, their ability to produce all those inflammatory molecules that contribute to inflammaging.
Oh, interesting.
To sort of circle it back around and tie it up.
I think you did some work on, I always pronounce this incorrectly, fisetin.
People call it fisetin. As long as you're not facetious about it, we don't really care. You can call it what you like.
So what do you, there's that one, fisetin and quercetin. Yeah. I'm not sure what else is out there. What have you been looking at?
So the original senolytic combination that was discovered in 2015 was a combination of dasatinib, which is a tyrosine kinase inhibitor that was used in chemotherapeutics, and this flavonoid called quercetin. So moving forward from there, when I joined the lab that I was working in for a postdoc, we wanted to find more potent versions of quercetin, and could they function as a senolytic on their own? And this was a huge group effort between us, people at the Mayo Clinic, and other institutions. And we saw that basically fisetin was more potent than quercetin. And then from there, embarked on a number of these preclinical studies where if you gave, acute dosing to a mouse, would it reduce their senescent cell burden? And it did. If you treated these mice that are short-lived, would it reduce their pathology or, their symptom scores and everything? And it did. And even if you take the drug away for a period of time, the biological benefit is maintained at least for a week or two, sort of showing that you could do these washout periods. And ideally, I think what the field of senescence wants to do is not have a drug that you take every single day. What we want to do is have an intermittent dosing, but we're still working out, obviously, all this, even in mice, let alone in humans, so that you would periodically dose, clear out your senescent cell burden, wait till it comes back to an appreciable level, and then treat again. And sort of you're avoiding the toxicity of chronic drug treatment. And what we saw in the old wild type mice was if you take old mice, so sort of these mice that are about 85 weeks old, they would be the equivalent of an elderly individual, and then put them on fisetin, just supplemented in the chow. It made them live a little bit longer, but it also reduced their senescent cell burden and many markers of pathology in their tissues, or improved some of their physiological function.
Not to get too deep in the weeds here, but
Sure.
How much fisetin were you giving? Like how much per? A mouse doesn't weigh a kilogram, but like how much you dosing them?
So that would be relevant if we were physically dosing them. So it was just food. It was in the chow, and the mice are allowed to eat as much chow as they want. It's called ad libitum. But we had compounded 500 parts per million fisetin in the chow. And I know there's a lot of people that have an interest in it through supplementation of diet. And there's, there is fisetin in strawberries and certain other fruits. You are not going to be able to eat enough strawberries to probably derive a biological benefit. If for clinical trials and things where fisetin is used, it's given as an oral supplement. Like you're not going to have enough strawberries to do it. And by the end of it, if you tried, you'd hate strawberries.
So give me an idea. If they're doing, with the clinical trials they're doing, what's kind of dosage? Are we talking massive quantities of this, or?
No, so it's intermittent dosing at a level for, I believe, the frailty trials and the COVID trials are 20 milligram per kilogram body weight. And
And
those
that's
can be
done
looked up. More
intermittently.
information on those trials can be looked up at clinicaltrials.gov. If you just put fisetin in the search bar, it'll populate all the studies that are ongoing with it.
And they're pulsing it, right? They're doing it
Yes.
like once a month or every couple of months or something like that.
It could be for a couple of days and then, 2 weeks off. It's best to go look at sort of the trial information because I think it can vary between trials. So,
Gotcha. Okay. Fascinating. And then you mentioned a chemotherapy drug that I'm going to
dasatinib,
mispronounce. Yes. I'm sorry, I talked over you. Say it again.
dasatinib. So
Dasatinib.
the reason that we used dasatinib was when it was first sort of understood and bioinformatically analyzed that these senescent cells, what survival pathways they upregulated, and this was work done at the Mayo Clinic by my friend Yi Zhu. She worked on basically, well, how do I target these pathways? Rather than creating new drugs to do it, let's repurpose these drugs. And dasatinib happened to target one of the key pathways they found in senescent cells, and quercetin some of the other. So, and that's why D plus Q, or dasatinib plus quercetin, became the first senolytic compound. It was driven by the bioinformatics.
Mm. I mean, I've heard of people doing this. I spoke with Brian Johnson a couple of weeks ago, the Blueprint guy, and I think he's doing this. He's a really extreme case. I like Brian, but he's a really extreme guy. I think he's doing it, similar to what you said, like twice a year for like a couple of days.
Yeah, I mean, I think we're still trying to figure out the dosing of senolytics, not only in humans, but in mice. And whenever this pops up is sort of a question about the clinic and what people are doing, I always like to sort of fall back on, I'm a preclinical scientist.
Okay.
Yeah, I'm a basic biologist. So if you want to ask me about a mouse, I can tell you about a mouse.
Fair enough. Tell me, so this is past research. What are you working on now?
Yeah, so I'm really interested in a couple of things. One of which is, many of the elderly mortality is driven through things like sepsis, so infections. And so, how does our aging immune system sort of enhance our chances for sepsis? And also, how does the relationship of an early septic event, what does it do to aging your immune system as well as the rest of your body? And then the other thing I like to study is, it's called inter-organ communication. So as our bodies age, all our tissues are aging at different times and at different rates. But your left calf muscle ages, your right calf muscle ages. Do they age at the same time? What's influencing it? And I and others really like to think in some ways that it's the immune system that could be influencing how we're aging across the different tissues of our body, because the immune cells and the things they produce are circulating all throughout our body. So, not only how does the immune system influence how our rest of our body ages, how does our rest of our body influence how the immune system ages? So what happens to somebody who, say, has a neurodegenerative disease like Alzheimer's disease or Parkinson's disease? What is the contribution from the brain to the rest of the periphery on aging as well, too? So I think these are really interesting questions that we're starting to address now.
How are you measuring aging in terms of, a specific organ system or a group of muscles? How do you decide that?
So I am a DNA repair biologist, and I study cellular senescence. So I like to look at markers of cellular senescence and markers of DNA damage. We also try to look at these other pillars of aging. So things like, well, what's going on with autophagy? Is epigenetic aging changes going on in those tissues. But, some of the gold standard is still physiology and function. So kidneys, you would measure things like glomerular filtration rate. So how well are the kidneys functioning and filtering things out? Do they have proteinuria? Things that are disruptive there. And then are there any pathology that can be done, pathological analysis? But if you're measuring things like muscle, you would be doing, exercise times or balance, so things that, real sort of measurements, not only the molecular measurements, but quality of life measurements. And these things can be done even in mice where, how long will a mouse go on a treadmill for? Or how long, if you put a mouse on a balance beam, will it maintain its balance for? Or for cognition, let's send a mouse through a maze. Or how's its memory?
Matt, you're putting mice on balance beams?
Yes.
That doesn't sound right.
Just slightly elevated, and you watch them walk on a balance beam, and
really?
you can measure, how long. Yeah. Or things like, you'll put a novel object in the middle of a cage. You'll see if they'll go actually look at it for recognition.
Interesting. I feel like there needs to be like some kind of like book or documentary, The Secret Life of Mice in Labs. Like,
yeah. Yeah, but there's so much information that we learn from them about the aging process, and two, how all these different interventions for aging, how they work. And maybe these interventions, if we're lucky, they work wholesale across the body, or there's tissue specificity, so that then these animal studies can tell us what combinations of therapeutics to use. Will this one work? Intervention A works really well on the liver and the kidneys. Intervention B works well on the lung. What about the brain?
Are you seeing systemic interventions that work?
We see some interventions that I would say things like rapamycin treatment. We've seen benefits across multiple tissues in the body. We know that with senolytics, we're able to reduce senescent cell burden and improve pathology in multiple organs in the body as well. But how can we do it better? Does this senolytic work better in the liver versus that senolytic, or, another intervention?
And are you seeing, as you're measuring all these different organ systems and such, are you seeing, I'm going to say like an aging burden, an organ dysfunction happening quicker than others? Like, so is the kidney the first one to go, or is it the brain or the muscles or anything like that?
I would say it's really variable. A lot of these old mice, like old people, they tend to have multi-organ failure. So, and it could be that, in this mouse may die of renal insufficiency. So the kidneys aren't working that well. This other mouse right next to it could be dying of cardiovascular disease. And another mouse beside it could have a tumor that's pressing on the lung.
So what you're describing to me then is a systemic failure. There's something going on through all of them. And are you thinking that, as you said earlier, this is related to senescent, these zombie cells within the immune function of the organism that affects all of this?
So I think there's two things: that we have the senescent cells that build up in our body with time. And this is just but one pillar of aging. There's probably contributions from the other pillars. However, we know that the immune system, when we're younger, is sufficient to clear out many of these senescent cells. So we're actually having a failure of clearance. So not only are our bodies sort of making more trash in our organs, but the immune system is sort of falling down on its job of taking out the trash, even though it's getting yelled at to do it.
So I know you work with mice and you work in a lab, but so I'm a human. That's what I'm really concerned about, is me, the human. What are the things that I should avoid doing to damage my, not to damage my DNA? So I don't really have a lot of control over, I have some control over my telomeres, but not that much. But there's a lot of things that if I chose to do them would damage my DNA? What are the things that I'm going to avoid doing?
Let's see. The easiest thing I would say is sun avoidance. Not to the level of you're a hermit, but so I also work with a rare disease patients that have this disease called xeroderma pigmentosum. And what it is they're effectively called children of the moon. So these children have mutations in enzymes that repair DNA damage, in particular, common forms of DNA damage that can be caused by UV light. So you or I, we can go out in the sun and get sunburned. It's going to hurt. It's not going to feel good. Well, these kids, they're getting these UV-based damage that's basically predisposing them to cancer. So compared to you or I, they have a 10,000-fold chance at increased skin cancer.
Oh, and when you're talking about UV damage outside the sun, my skin, does this, if I damaged my skin from too much UV light, does that also affect the rest of my body in some way? So is it just the skin we're talking about, or are we talking about everything?
You're talking predominantly the skin, but you can get circulating inflammation as well from it. But there's many other things, not just that, things that we've seen before of, if you put a mouse on a high fat diet, really, really high fat diet, or it could be isocaloric, it's just a lot of fat in it. Or you could use something called the total Western diet, which I like to affectionately call the McDonald's or the cheesecake diet, where it's, malnutritious, but high in fats and sugars, that these mice will develop an enhanced senescent cell burden throughout their tissues. They're developing increased reactive oxygen species.
So I'm going to take this a little further. Going to McDonald's damages my DNA. Did I get that right?
I would not.
I'm going to get sued by DNA.
Or by, yeah. We're going to get sued by McDonald's. Ba-da-ba-ba-da, we're done. No, but as we jokingly say that we're trying to push the science forward for interventions for aging, whether they be pharmacologics, biologics, cell transplantations. Could epigenetic reprogramming work out? By and large, the things that we can affect in our everyday life are things like diet and exercise. We also know too that chronic stress has been shown to shorten the life. Social stress has been shown to shorten the lifespan of mice. We even see that social stress can even have an impact on our immune function.
Yeah, absolutely. So we're sort of back to like the four basics, right? It's what are you eating, how are you moving, are you sleeping well, and how are you dealing with your stress? Getting that under control, and obviously, stay out of the sun. Don't get a lot of radiation. Things like this would seem like a good way to avoid the DNA damage, which is going to cause the zombie cells, which is going to cause inflammation.
Correct.
Okay, super. So as we look forward here, Matt, are we thinking? I've spoken to a lot of people about sort of health span expansion, possibly lifespan expansion. That hasn't happened yet. It might happen. But I think there's maybe 4 or 5 really promising fields that people are looking at, and senolytics is in there. Are we looking towards a future here where there's some combination of drugs that will just I forget what you had a really good word for, not necessarily removing the senescent cells, but making them inactive so they don't cause any more damage. So is that where we're going with this?
I think we're going at 2 fronts. We're developing things that can we remove the pathogenic cells of aging, or can we neutralize their effects? But beyond that, as we go towards health span's a really vague term, and it's really an amorphous target. We're still trying to figure out what do we measure for health span, both in humans and mice. And what's the best metrics to use. And I think we're starting to learn, as we become more health focused as sort of a nation and a world, how do we longitudinally measure those things in people so that we get early indications of, okay, you're not feeling sick yet, but your biomarkers for aging that we feel are pretty reproducible and robust, they're starting to show a negative inflection. Like things are starting to slip molecularly because the molecular changes will predate the physical changes or the functional changes. And that may be a point at which you're ripe for intervention. So it's also where do we have the biggest windows of effect we're starting to learn too.
Yeah, I'm hoping the biggest window of effect is still open for me.
Yeah, we all do.
Matt, thank you for your time today. Is there anything you want to leave people with today?
I'm really excited about the biology of aging. I hope you are too. There's a lot of resources and things out in the field if you're interested in it. There's two organizations in the US I always promote because I'm a member of them, the American Aging Association and the Gerontological Society of America. They're basically built on the backs of academic basic science researchers as well as clinicians. And they do have some involvement of people from biotech and aging biotech.
Fascinating. Thank you so much for being with us today, Matt. I really appreciate it. Rising star in the field. It's really a privilege to have you on today.
Thank you. It was a great time being here. I really enjoyed it.
That was wonderful. Matt really is like the guy in the field of senolytics. His research is what a lot of people are referencing. And, you know, as we talk to a number of these folks out there in the field of aging, and, you know, if you believe that aging is a disease or, you know, it's certainly an indicator of future disease, it seems like there's, you know, maybe like 4 or 5 really promising technologies, and who knows, they may overlap. We don't know. But, you know, the more that we talk to people like this, it really seems like, you know, we had Mike Roizen on maybe 6 months ago talking about how 90 is going to be the new 40. You know, I think there's a pretty good chance of that. So we're going to get to Just Try This in just a second after a quick word from our sponsor. Today's show is also sponsored by Element, spelled LMNT. Element is an electrolyte drink that contains the exact ratios of the electrolytes sodium, magnesium, and potassium to optimize our cellular functioning for mental and physical performance. Most of us understand that, you know, we need to stay hydrated. But what a lot of people don't realize is just pounding water isn't going to cut it. In order for our cells to function properly, they need sodium, potassium, and magnesium in the right doses. Element has perfected the balance. Now, of course, people with prehypertension or hypertension need to be careful about their sodium intake. But for most of us who are mindful about eating clean, unprocessed food most of the time, we may not be getting enough sodium, potassium, or magnesium. That's why I drink a packet of Element each day. If you'd like to try Element, go to drinkelement.com/ageist, that's drinklmnt.com/ageist, and receive a free 8-serving sample pack with any purchase. Let me know what your favorite flavor is. I'm into citrus salt. What's yours? So this week on Just Try This, I recommend reading literature. I know that might sound a little old-fashioned, you know, in the world of TikTok and streaming and all that, but there's something wonderful about long-form fiction literature because when we engage with it, it goes on for quite a while, right? It's not 15 seconds of TikTok or an hour of television or 3 hours in a movie. I mean, it goes on for like several days. And if you're like me, a slow reader, maybe it goes on for a month. You know, and however long it takes you to read the book, you are involved with the characters, you're involved with the story, you're transported to another place, to another time that's perhaps nothing like where you are now. And I like this enlarging of the imagination, the enlarging of our experience without really going anywhere. So that's my suggestion. This week, get yourself a fiction book and read it just for the fun of it. Thanks, everyone, for joining us on the Super Age podcast this week. As always, you have the opportunity to leave us up to a 5-star review. Have you done that yet? I know we're getting a lot of downloads, and not all you guys are leaving us 5-star reviews. You're not leaving us any reviews at all. We would love to get your review. You can leave a comment or Hey, if you want to contact me, david@superage.com, and I will get back to you promptly, directly, and personally. Next week, we got another great show coming up. Until then, have a wonderful week, and maybe read a book. We'll see you then. Take care.